So in the last few sessions, we've been talking about different stages of stellar evolution. We talked about star birth, the evolution of low mass stars, the evolution of high mass stars. What we want to focus on for these next couple short sessions are the different types of dead stars. We know that during the end of these stars' lives, for low mass stars, the planetary nebula ejects away a lot of material. Or for high mass stars, the supernova violently explodes away that outer material. But these all tend to leave behind some kind of object. So we're going to be focusing a little bit on what each of these different objects are like and their general properties. And these are going to be some of the weirdest objects that we know of in the entire universe. So again, these dead stars, low mass stars are going to leave behind white dwarfs after that planetary nebula phase. High mass stars that violently explode as supernova, well, depending on the mass of the star core that's left behind, it's either going to leave behind a neutron star or a black hole. And again, it's important for these different types of dead stars, it's important to remember that the primary thing that determines the properties of a star and how that star is going to evolve was the starting mass of the star. Low mass stars follow a certain trajectory and lead to a certain kind of object. High mass stars evolve differently. If the star has too low of a mass, it won't even become a star. It'll just be a brown dwarf. And again, that mass of the star is primarily what determines the physical properties it's going to have and how it's going to evolve. Now, as we're going through these different types of dead stars, it's going to be helpful to be able to quickly compare and contrast some of their properties. So I've posted this dead star memories matrix, dead stars memory matrix, that talks about white dwarfs, neutron stars, and black holes. And you can fill out the details on things like what's the progenitor stage, what's the previous stage before we get one of these objects, what mass ranges do we have, how are the sizes of these objects going to compare, their densities, the future for the isolated dead stars, possible futures if it's in a close binary system, and some important terms that we're going to be defining in these next couple sessions about these white dwarfs, neutron stars, and black holes. So for example, for the white dwarf, we said the progenitor stage for the white dwarf is going to be the planetary nebula, the relatively gentle expulsion of the outer layers of the star. For neutron stars and black holes, the progenitor is going to be that supernova event, that very violent exploding away of those outer layers. So again, I do recommend downloading this or making a copy of this in your notes and just being able to quickly compare and contrast the different properties of these different types of dead stars. So for this session specifically, we're going to be talking about the white dwarfs. This is the exposed core of a low mass star. So it's the ending stage for low mass stars. And these are primarily composed of carbon and oxygen. We said that low mass stars, they fuse hydrogen into helium and then helium into carbon through that triple alpha process. But these low mass stars aren't really massive enough to start fusing carbon, or maybe they might fuse a little bit into oxygen. But these low mass stars, the cores that are left behind, it's going to reach carbon or oxygen before the star can no longer reach the temperatures and densities necessary to actually undergo further fusion. These objects, as we've mentioned a couple of times before, these white dwarfs are supported by this electron degeneracy pressure. So supported by electron degeneracy pressure. Again, we've talked about this a couple of times, but worth repeating, that the electrons are so smushed together, the fact that those electrons don't want to be in the same quantum state is the thing that is stopping this star from further collapse. And one of the key things that we're going to be focused on here is this degeneracy pressure is unaffected by temperature. So this pressure is unaffected by temperature. Basically, if I change the temperature of this white dwarf, it's not going to expand or contract owing to changes in temperature. And this is actually going to have some very, very serious consequences in just a little bit. These white dwarf masses are less than 1.4 solar masses. So mass is under 1.4 times the mass of the sun. So whenever you see this symbol, M with a little circle and a dot, that means solar masses. And if the white dwarf exceeds this mass, we're going to talk about some consequences to that, because this electron degeneracy pressure fails, and we're going to get something called a white dwarf supernova. We'll be talking about that in a little bit, but remember this 1.4 solar mass limit. One of the weird things about these white dwarfs is that the more massive they are, the smaller they are in size. These are all typically around the size of the Earth. So even though they can be up to 1.4 times the mass of our sun, their size is approximately the size of the Earth. This means we've got a mass comparable to the mass of our sun compressed down into a region around the volume of the Earth. That means that this material is exceedingly dense. This is basically as compressed as you can make ordinary material that's made up of atoms. So again, we've got a mass greater than the sun's, sun compressed down into a volume similar to Earth. A 1 solar mass white dwarf would be slightly larger than the Earth. A 1.3 solar mass white dwarf is actually a little bit smaller than the Earth. As we add more mass, it gets more and more compressed, and that electron degeneracy pressure has to work even harder in order to stop any further collapse. In terms of the density, 1 teaspoon of this material, if I had just a little teaspoon of this white dwarf material, it would have the same mass as a fully loaded semi-truck. This is incredibly dense material. If you actually had that material here, it would actually violently explode, because that material is so compressed, unless it's being held together by that extremely strong gravitational force, this thing would just detonate itself. So density, 1 teaspoon is around the mass of a truck. This also means if I have a huge amount of mass held in a very, very small location, if you're close by that object, there is an incredibly strong gravitational field near its surface. So strong that the escape velocity from the surface of one of these white dwarfs would be around 2% of the speed of light. If you wanted to launch yourself off of one of these white dwarfs, you'd have to be going at around 2% the speed of light in order to escape its gravitational pull. For comparison, the escape velocity of the Earth is around 11 kilometers per second. 2% of the speed of light, that's closer to 6,000 kilometers per second. And let me just kind of point out this as well. When we talked about our gravitational force equation, so the force of gravity is equal to G times the masses that are interacting divided by the distance squared. What makes the gravity on the surface of these objects so strong is not that they have a particularly high mass. No, the mass is still around the mass of the sun. What makes the force of gravity around these objects so strong is that those masses are compressed into a very, very small distance. So the mass hasn't really changed. In fact, the star that formed this white dwarf, it's actually expelled material away before forming this white dwarf. So the mass has actually gone down. What the problem is for getting close to this object, if I am very close, you can get very close to one of these relatively small objects. So we can get very close. For all of these different types of dead stars, their extremely strong gravitational fields near the surfaces of these objects is not owing to the fact that they have a very large mass. They don't. This one's around the mass of the sun. It's that these objects are so compressed, you can get really, really close to their centers, and then the gravitational forces become very, very extreme. So here's an example. This is Sirius B. Sirius A is one of the brighter stars. Actually, I think it's the brightest star in the night sky, but it's actually a binary star system. We have Sirius A, main sequence star, and Sirius B is a white dwarf. This white dwarf is just a little bit more massive than our sun, a little bit smaller than the Earth. Its density is 3 million times the density of water. It's got a very high surface temperature, very low luminosity. So on that HR diagram, when we had luminosity and spectral type from OB, AF, GKM, so from high temperature to low temperature, those white dwarfs are in the bottom left part of that diagram. Low luminosity, but a very, very high surface temperature because they have a, and those two match up only because they have a very, very small size. And Sirius B, its escape velocity would be about 2.3% the speed of light. So this white dwarf, what would happen if it was just an isolated white dwarf in space? Well, it's still radiating away some of its thermal energy. So it's still shining. It doesn't have a high luminosity, so it's not radiating this energy away very quickly, but it is still doing that. And over many, many billions of years, like we're talking longer than the current age of the universe, eventually that should radiate away all the remaining thermal energy and leave behind a black dwarf. But what happens if we are in a binary system? Let's talk about binary systems and accretion. So we've talked about binary stars where we have two stars that are orbiting around each other. Well, maybe one of those stars has collapsed into a white dwarf. So let's say this is our white dwarf, and we've still got this other star, and they're still orbiting around each other. Let's say that that second star, as these objects are orbiting around each other, they'll just continue on in their orbits as normal. But let's say this second star, let's say this one starts expanding as a red giant. So starts expanding as a red giant. So the outer layers of this star start puffing outwards and push some of those outer layers towards the white dwarf. Remember, just a minute ago, I said the force of gravity around these different types of dead stars, the force of gravity isn't strong because those objects are particularly massive. Those forces can get strong if some material gets really close to these objects, because it's when those distances become small that these gravitational forces become very, very large. So in the case of this white dwarf, if this star starts expanding as a red giant and starts pulling in material, well, now that star, now the outer layers of this star are close enough to the white dwarf for that white dwarf to take over, start pulling in that material, and what tends to happen is it will pull that material into what we call an accretion disk. So again, that material is falling into this white dwarf, and as those layers are kind of rubbing against each other, they're going to dramatically heat up. So as those layers of material are gradually falling into that white dwarf, those layers of gases are kind of rubbing against each other and can generate very, very high amounts of energy, very, very high temperatures, and will end up glowing very, very brightly. We'll see some effects of this a little bit later. We're also going to see that this kind of accretion can happen for any type of dead star. We're specifically talking about white dwarfs right now, but this can occur if we've got a neutron star here. So maybe we have a neutron star instead of a white dwarf, or if we have a black hole. All of those different kinds of dead stars can have this accretion process begin if some of the gases from the nearby star, some of the material from that star gets puffed up away from the star and gets a little bit too close. Well, then that dead star can start to capture it. And again, this is not because these dead star masses have to be particularly large. It's because these gases are getting too close. So these white dwarfs, we said that they do not have a high enough temperature and density in order to undergo the fusion of carbon or oxygen or some of those heavier elements. However, if this thing is pulling in material from its nearby star, it's probably pulling in hydrogen. And these stars still have enough energy to start fusing hydrogen. In fact, when hydrogen starts building up on the surfaces of these white dwarfs and more hydrogen is violently smashing into it, you can actually get these kind of flare-ups, almost like a grease fire on a grill, where very, very quickly that region starts to go through hydrogen fusion on the surface, and we can actually see this nova effect of this hydrogen that has fallen onto the white dwarf. It suddenly starts to go through fusion, give off a huge amount of energy, a bright burst of energy that we can actually detect. So the falling material, the falling hydrogen material can undergo fusion on the surface and start fusing on the surface. And we call this a nova. In fact, we've seen white dwarf binary systems that have white dwarfs, where that white dwarf is accreting material and it flares up repeatedly. I don't know how to pronounce this particular star name, but this has gone through novas in 1890, 1902, 1920, 1944, 66, and the most recent one, at least that I know of, was in 2011, where we get this flare-up of hydrogen fusion on the surface, and it can send out these blobs of material into space. These little speckles that you see around it are previous blobs of material that have been ejected from the star due to these nova events. But there's something even more drastic that can happen. Because remember, we said that these white dwarfs, they can only go up to 1.4 solar masses. That is the limit where the electron degeneracy pressure that was supporting this star against collapse, it can't support the star against collapse anymore. So if it passes this limit, and this actually has a named the Chandrasekhar limit. I'm not going to expect people to memorize that, but let me just write that down. The Chandrasekhar limit, where again, that electron degeneracy pressure will no longer be able to support the star against collapse. So what's going to happen when this electron degeneracy pressure fails? Well, that star is going to start to collapse and produce higher temperatures and higher densities, finally reaching the part where carbon and oxygen and some of those heavier elements can start to fuse. So the star begins to collapse, generates higher temperatures and densities, and starts some new fusion reactions. Under normal circumstances, when fusion starts in the core of a star, that fusion rate causes the star to expand a little bit, or causes the core to expand a little bit, and that reigns in the fusion rate. But this star had been supported by the electron degeneracy pressure, which is unaffected by temperature. So as this white dwarf starts to collapse and a new fusion reaction occurs, that increases the temperature, but it doesn't cause the star to expand. So that increase in temperature is going to cause an increase in the fusion rate. That increased fusion rate is still not going to allow the star to expand. And we get this runaway reaction. Inside of this star, the temperature skyrockets, and we get what's called a white dwarf supernova. So let me write this one down. The white dwarf supernova. Again, this white dwarf, if it has accreted some material from a neighboring star, if it accretes too much material and passes over this limit, fusion is going to, the electron degeneracy pressure fails, so it accretes too much material. So past that 1.4 solar masses. And then fusion erupts throughout the star. Through the white dwarf. The entire thing is going through a fusion reaction simultaneously. And again, this skyrocketing temperature eventually causes the entire white dwarf to completely obliterate itself, leaving nothing behind except this expanding cap cloud of dust and gas. These white dwarf supernovas, these are some of the brightest supernovas that we see, some of the brightest events in space. So extremely bright. And uniquely identifiable. There's a couple of ways that we can identify that it's a white dwarf supernova. First off, they have very characteristic light curves. The brightness will increase, and then over the course of a couple of months, the brightness will go down in a very characteristic pattern. These are also identifiable from the absence of hydrogen spectral lines. This exploding star is primarily carbon and oxygen. It's one of the only objects that we'll talk about in the course that aren't 3/4 hydrogen, 1/4 helium, 2% other stuff. These ones are primarily oxygen and carbon, so they're missing those hydrogen lines, so they can be unambiguously identified. They're also all exploding at the same mass. So occur at the same mass. Which means they all have approximately the same luminosity. Again, these things are ridiculously bright. This is a galaxy, and that one white dwarf supernova, this is a 3-month time lapse, so you see it gets brighter and then gets dimmer with a very characteristic pattern. In this 3-month time loop, that white dwarf supernova, that one exploding white dwarf, is outshining the entire rest of its host galaxy. This before and after, I don't know if I really needed to put a little arrow on here saying where is the difference between these two pictures. But again, these are incredibly, incredibly bright objects. And again, since it's this Chandrasekhar limit, this 1.4 solar mass limit that they all explode at, they're all exploding at around the same mass limit. So they all have approximately the same luminosity, and this is incredibly useful for astronomers. Since they all have the same peak luminosity, if I observe one of these white dwarf supernovas occur in a galaxy, and I can identify it as a white dwarf supernova, I know its luminosity, I know its apparent brightness, so we can use this equation or the rearranged version of it, that the distance is the square root of luminosity over 4 pi times the brightness. If we know the luminosity, since it's a white dwarf supernova, and we know the apparent brightness, we can calculate what is the distance to this particular white dwarf supernova. This kind of an object where we know its luminosity, we have a way of uniquely identifying its luminosity and know the brightness, we call these standard candles. And this is another way that we measure the distances to very, very distant galaxies. If we see one of these white dwarfs go off, white dwarf supernovas in one of these galaxies, we can use it to measure the distances to galaxies that could be in the billions of light years away from us. So this is an incredibly useful tool for astronomers and another way that we measure cosmic distances. So that kind of finishes up our talk about the white dwarfs, and we'll talk about neutron stars and black holes in one of the next sessions.